Did I lose most of you, or you're doing okay? Okay. What? Oh, okay, got you. This one, right? Screen, okay. I'll pay attention to that. So, glad you are still here after first lecture, okay? So, we did some serious math, okay? So, now let's continue. The second thing we want to check is sometimes called the positivity. So now I want you to look at the equation for the target cell. So does this model make sense? We already find out one problem with the model, right? What's the other problem? So we have t is equal to rho t minus delta v minus delta t. Okay. So when I say positivity, which means this number should be always greater than or equal to 0, because the number of cells cannot be negative, right? It can only be positive or 0. 0 is fine, okay? So let's check this one. What's the problem with this one? So if we don't have infection, then this model becomes what? This term is gone, right? What's left is now under normal condition, okay, if you want to this number be non-negative, what do you need to do? This rate has to be not only higher, should be much higher, because this one is exponential death, right? This is a constant growth. So you have to satisfy sort of a condition like to make it positive. Okay, so this one is actually implicit. Okay, when you create a model, okay, this one actually is implicit. Sometimes you need to be careful. If you create a model that gives you a negative cell number, that will not make any sense, okay, to people. So pay attention to this kind of thing. Okay, that's the second thing you should check. So now, still this model, we give it a second try, okay? Ask yourself, the first question is, did we miss any major players in this game? We're talking about the infection, okay? Cell infection by virus. So any major component we missed. We have target cells in the model. We have viral particles in the model. Anything else? Yeah, infected cells. Why shouldn't we put the infected cells in the model? There's no reason we don't put that in the model. It is important. Why? When we examine the model in a previous lecture, we see that this term, the V should be replaced by the infected cell. So actually, we don't only have two equations. We don't have the actual equations for T star. So that's why we need to actually bring this back. Okay. Now, if we have, okay, the T star, we have a three variable system. So how we do the modeling? Let's reconsider, okay, this infection model again, okay. I actually intentionally start with the wrong model, okay. One variable missing, and some terms have problems. Now let's do it right, okay. Three variables. And what do? we do the same thing. Now we have the players. Let's just lay out their behavior, okay, like we do before. First, we have exponential growth of t. Right? And we have a loss of target cells due to infection. I will change the notation a little bit, okay, from now. This makes sense, right? We just talked about it should be proportional to t and also two-way, the infection rate, okay? And this is a loss of t due to infection. So if we also look at the T star now, okay, so what will cause the increase of T star, infected cell? Infection, right? So once our target cell is infected, how many infected cells do we get? One cell is infected. How many infected cells do we get? One, right? So the increase rate should be equal to this one. So you lost that many uninfected cells, you get this many infected cells. So this will be the increase of T star due to infection.
Second one equations differ from what you have written in the earlier example. Where you have a loss of T infection, it's a different equation. So is there any reason why you changed it in the previous example?
In the previous example, we used is that right? Delta VV. And we talked about the unit is not consistent. And we need add a T here.
Yes.
So this term is just that term, but I just changed the notation for this one. Okay. I replaced it with beta. Okay. It's just my personal preference. Okay. I use delta actually. Usually I use delta to denote depth. Okay. And
My curiosity just want to know why you changed.
Oh yeah, that's my personal issue. So now we know this is an increase rate of T star, okay, due to infection. So will the infected cells die? Yes. Yeah, they will. Actually, they usually die faster than the healthy cells, right? So let's say due to death. So, you know, CTL, they can kill the infected cells, right? That's why they die faster. Okay. So now, make it formal. Okay. I put a sign, okay, in front of each term. So later, you just include the sign and the term in the model, then you're done. So now we did things for T, we did things for T star. So what's the next thing we need to do? Reverse, right? So reverse will be regenerated. Okay. Thank you. Reverse will be regenerated by what? Infected cells, right? So this production will be, I change the notation a little bit, okay? I use pi to denote the production rate. And now it should be proportional to the number of infected cells, because only infected cells can reproduce virus. So this is production of V. Now, will viral particles disappear or be neutralized? Yeah, it will. If you have an antibody, okay, they will neutralize the viral particles, and they're gonna disappear from the system. So that rate is proportional to what? To V itself, right? So let's put here. Disappearance of V, okay. Sorry about this minus sign. Okay, now we specified all the possible behavior of the three different particles, okay? What's the next step? We just put them in the equation, okay? So what do we have for T? We have growth minus infection, okay? What do we have for T star is increase due to infection and minus the death. Similarly for V, we have regeneration subtract neutralization. Okay, does that make sense? So do you want to do a unit check again? Yes? Okay. So let's see whether this model is consistent or not. This one we don't have problem, right? Exponential growth. We have talked about the exponential growth many times. And infection, now the unit of beta is again per hour per particle, right? Like we mentioned before. So this unit multiply the unit of T, you get what? You get the cell per hour per particle, right? Then I multiply V, you get cancel the particle out, you get the cell per hour, which is the unit of derivative of T. The unit of T is the cell per hour. Now we get a consistent unit, right? So we're okay now. So similarly, you can check this term, okay? And I cannot see any problem, okay, for now, for this term, okay? So how about the positivity? So we talked about the positivity for the round model, okay? How about this one? So now if V becomes 0, what do we get? For this equation, we get P star is equal to, so just growth, okay? It will be positive automatically, okay? And how about T star? If there is no infection, T star will be 0. And this term is gone, right? And the infected cells will only die. Okay, and this one is 0 pi T star minus 0. Okay, from the third equation, you can infer that the T star will become 0. Right? The T star is 0, then this is 0, this is 0. Okay, it's gone from the system. Now you only have a healthy target cell, and they will grow. Of course, depends on your growth model. You probably will have a saturation. Okay, then this parameter will become 0. Okay. So now we check the positivity. We don't have any issue, right? So this positivity requirement automatically satisfied.
So this is the case where there is no infection.
Yeah, no infection. Yeah. So now I actually want to talk a little bit more about the term infection term. Okay, we construct the infection in this way, the infection term in this way. Okay. However, the derivation of this term actually comes from the so-called law of mass action. Okay. It's originally actually developed to describe the chemical reaction, okay, between chemical compounds or particles. So in this law of mass action, we assume that these particles are well mixed, so we don't consider the spatial difference. Okay, so we assume the spatial homogeneity. Okay. If we look at this simple reaction, reactants A and B can produce AB. And the law of mass action suggests that at the equilibrium, the following rate is constant. That is, the number of AB divided the product of A and B is constant. Because it's at equilibrium, right? That's one thing. But if we break this reaction down, you will see why. We know that many reactions that are reversible. Okay, so you have a forward reaction. You also have a backward. So this is like association. This is like a dissociation. Okay, so this association rate is Ka. This association rate is Kd. Now, the forward reaction rate is what? Should be the K multiply the number of A and the number of B, right? However, actually people publish a few papers to get there, okay? Originally, this is not a form. They originally use this form. Okay, this is a general form. You have a power here. Then later, people actually simplified to this form. Says this one is okay. Okay, so you can imagine that people can publish paper, okay, just for this, okay, back in 1940s, okay. So the backward rate is what? It should be Kd multiply what? Number of AB. Okay, now because it's at equilibrium, the forward rate should be equal to the backward rate. That's these two divide, the ratio should be constant. So that's what you see there. You just flip this over, the ratio, this one flip over, you still get a constant. Okay, that's why you get a constant. So now let's talk about our infection term. Okay, just this one term. Okay. No.
For the equilibrium?
No.
C. Okay.
You see? My answer should not be no. Should be not necessary. Okay, that's necessarily true. Right? What we just derived is this one. Now let's remove K and Kd to the right hand side. You get that. Now a constant multiply. This is a constant rate. It's still constant.
Okay.
So that's what it means. Okay, it doesn't mean these two has to be equal. Okay, they can be, but it's not required. Okay. Okay, so now let's just look back to our inflection term. Okay. Beta PV. So why people eventually simplify this term like first order, or just proportional to the product of the two variables? For a simple reason, if you have one particle in a system of A and one particle of B, in your system, and let's say during delta t, a short time interval, A has a 10% chance to meet B. Okay. Sorry. So it's just our assumption. If I have one particle of A, one particle of B, given a time window, A has a 10% chance to meet B during our time window. Why if I have 1A but 3B? Although I draw this bigger, the space is the same. I'm not increasing the space. So still during delta t, what's the chance that A can meet one of the B? That's 30%, right? So which means the rate will increase as the number of B increase, and it's sort of a linear relationship, right? 3 multiplied 10% is linearly proportional. Then now I do the same thing to A. I now have 3A, 3B. So again, the same time interval. What is the chance that 1B can meet 1A? Here I talk about the probability that 1A can meet 1B. Now I ask the question, what is the chance that 1B can meet 1A? We don't know that. Back to here. If A has a 10% probability to meet B, which means B also has 10% of probability to meet A, right? So again, for 1B to meet 1A, you still have a 30% chance. That's why here we say if we increase number of B, this rate will increase. Here we say if A increase, this rate will also increase. And both are linearly. That's why eventually we do this. Does that make sense? Any question? Instead of staring at me, ask the question.
So, are you still the same 30%?
Because I asked the question. Here the question is what's the chance of 1A meet 1B? Here I ask the question, what's the chance that 1B meet 1A? I'm not asking the total. So
you're basically justifying why you have in that term T and V.
Yeah,
right?
yeah, and why I can write just a linear relationship. Instead of put 1.5 or 2.0 here.
When you're defining A and B, are cells and
Particles, any particle. A can be cells, B can be wires. So same thing. If you have 11B, you increase the chance, but the chance will not be greater than 100, right?
Yeah.
You have 1. So.
But if you have 11A but still 3B, it's going to be 30%.
What?
In that last one, if you have 11A's but still 3B, it's going to be 30%.
For B, yes, but for A is not. Okay, so you can play with this tool, but this one just to show you, okay, why we derive the model in this way. Okay, so is that clear? So now let's move away from the within host infection. Okay, let's talk about the epidemics. Okay, so now will be the third set of models we want to introduce. So again, we start with the simplest model. It's called the SI model. So we classify the population into two categories. One is called susceptible, or one is called infective. Okay. And the susceptible is healthy, but can be infected by the eye. And how we model the number of the infective. So I already wrote down the equation, okay? But let's do the math on the board, okay? So again, I start with this difference, okay? So what factors will cause the change in the number of I? Any?
Rate of infection.
Real infection?
Yeah,
Okay. So
number of
if the infected more susceptible, will this lead to an increase or decrease of I? So
increase.
increase, right? The question is, if the infected more susceptible subjects, will the number of I increase or decrease? Increase. So we have a positive term here. Due to infection, we already know, okay, for the infection, we can use the law of mass action. Okay, beta SI multiply delta T, right? Now, divide delta T, you get so, is that simple? No? It's not simple? We already talked about the infection model. Now back to this one-term model. Okay, it should be simple right now. Okay. So although we actually went through a long way, okay, to get there, okay. But now we know if we model the infection term, we can use the law of mass action and write the term in this way. Okay. So we got this equation, and from now on, instead of just mathematics, okay, actually, let's start to use diagram, okay, to help us. So how we create a diagram that can describe the behavior or the interactions between S and I. So we have S here, right? And they will become infective due to infection. At what rate? Right? This is how many subjects will become infective per unit time. Okay? So this is a diagram for this equation. Like I mentioned the other first day, you can actually match, okay, the diagram and the equation. They are talking about the same thing, just to use a different language. Okay. So this afternoon, actually, we're going to learn how to create a diagram using some packaging. And that package actually can convert the diagram into equations. So you don't have to write equations. You just draw a diagram. Does that sound wonderful? But don't draw the diagram wrong, okay? That's all. So that's also the reason why I start to talk about diagram, okay? So this is a diagram for this simple model. change your mindset, okay? Now start to think this model is simple, okay? Instead of think this model is complicated, okay? Okay, so that's our first epidemics model, okay? So let's do something with this model. If we assume no birth and also no death in this population, then the total number of the S and I should be a constant. Right? So now, if it's a constant, I can rewrite my model in this way. Beta Si, what's S? N minus I. Right? Under this assumption, okay. Then multiply I. Okay. Then I can take N out, and then I can get this equation. Right? I move I to here, and take N out of this part. Then you get 1 minus I over N. So the reason I'm doing this, for now you see there's a limit. There's upper limit, like we did for the growth model, right? So at most you can infect the whole population, which means I is equal to N. Okay, you cannot infect any more, okay, because that's the total number available. Also, we have N here, and this one actually has a name, okay? It's called carrying capability. Okay. So the N, okay, number N, okay, is called carrying capability, which means the maximum number you can have, okay, in a population. Question? No? Good. So now let's, again, I'm going to do the same thing. I'm going to add factors one by one to make this model more realistic, okay? So for now, we consider the S and I. So how about the infective can recover and then become susceptible again? That actually happens to what? RSV, right? So RSV, you cannot, right now we don't have actually a very effective vaccine, okay, for it. So you get infected this year, this time, you will still get infected next time, okay? So I will become S again, so after some time. So how we model this? Okay, we start from the change, okay? So the infection part is the same, actually, right? Due to infection, the number of infected will increase, okay? But now, the infective can also recover and become susceptible S again, okay? So what I need to do is subtract, right? Subtract the number that become S. So let's use gamma to denote the recurring rate, then multiply I, and also delta T. Okay. So what's the next thing to do? Divide the delta T at both sides. Then you get does that make sense? So let's just draw a diagram, okay, for this one. So what will be the diagram? by what? Now I recovered and become S. So it should be only proportional to I itself. S will not help them to recover, right? That's the rationale. So if I draw a diagram, you have S, we have I. We know that S becomes I at a rate beta Si, and I can also recover at a rate gamma I, right? That's a diagram. So again, we can assume there's no death and there's no birth, and we have the sum of S and I being a constant, right? So now, what will be my equation for S? We just talked about the equations for I, right? What will be my equations for S? By looking at this diagram. So we assume that no birth, no death, okay? So S, of course, S is equal to n minus I. That's for sure. How about the differential equation for S? We can do the same thing, right? The increase of S due to the recurring, right? One I recovered, then you get a one susceptible. So you have a gamma I here, right? And the loss of S is due to infection. And if you lost one S, you get one I, which means this term should be the same as here. So now you divide. This should be multiply delta T, okay? Now you just divide the delta T, okay, at both sides. Then you get okay, that's actually a differential equation for S. So now let's check whether this assumption holds. We assume that S plus I is a constant, no birth, no death. So what we can do is add these two equations together, okay? This is the equation for T, for I, okay, sorry, not T. So if we add them together, what do we get? We have S dot plus I dot, and this one canceled out, this one canceled out, equals to 0. The derivative is 0, which means this number is constant, right? So n, this one is actually to n dot, right? Because S plus I equals to n. So n dot is 0, which means n is a constant. Okay, so it holds. Now, let's actually do something, okay, with this model. We have been talking about how to construct the model, okay? Now, you'll get a little bit more comfortable, okay, with this kind of model construction, right? Although maybe not very familiar yet, but you will be, okay, if you keep practice by following this kind of procedure. Now, actually, I would like to start, since we have the model, okay, I would like to start to play with the model. So what is the prediction, okay, we can do using this model? So here I ask the question, okay, how can we tell from the model whether the disease will disappear or become endemic? So here's our model. My question is, how do we know that this disease will become endemic or just disappear?
We want to drive it towards the right side of the reaction.
Yep.
And then we want that DSI to be higher.
Yeah. So first we need to interpret this, question into a mathematical expression, right? So what does it mean by endemic? I should be increasing or stay the same, right? If I is decreasing, then it will disappear, right? So disappearance means I will decrease. So when will I decrease? Remember, if I draw a straight line, okay, xt versus t, if x decrease as t increase, then the slope is negative. Similarly, if xt increase as t increase, the slope should be positive. We use the same concept here. So we actually know the slope. Okay, this is the equation for the slope. So if I decrease, which means the slope of t should be negative. If it's endemic, which means I, derivative of the slope of I should be positive.
Could it be also equal to 0?
Yep, it can be also equal to 0. If you want the infection stay. Okay. So that's actually the interpretation, okay, how we match the question, okay, the description in text, okay, with the mathematics. You need to do that a lot, actually. When you do the modeling, okay. So convert the description, okay, into a mathematical expression. So now we know that that's what we're looking for. Then let's look at this case first, okay? Disappearance. So if the slope is negative, then the disease will disappear. Then what's the slope here? The slope actually is beta Si minus gamma I. Right? That's our equation. So this one is negative. So I can be cancelled out, right? Because the right-hand side is 0. Okay, just remove the I. Then what we get is if you actually you move the gamma I to the right-hand side, you get this. Okay, beta Si is less than gamma I. And then you cancel the I out. Okay, then what do you get? Beta S gamma less than 1. So if I can satisfy this inequality, then I know the disease will disappear. Right? So for simplicity, because we know n is a constant, right? Then I just use this relationship. No, it's gamma. Because S is less than or equal to n. So this inequality will hold, always hold, right? Because total is n. And if we know if this number is less than 1, then this number must be also less than 1, right? Because if a big number is less than 1, then a smaller number will, of course, also less than 1. So that's why eventually we define this as a so-called reproductive ratio. Okay. I denote as R0. So once we define this ratio, we know that if this ratio is less than 1, this disease will be gone. So now we answer the question, okay? Under what condition you will have endemics, or under what conditions you will have disappearance? So under this condition, you have a disappearance. And if this ratio is greater than or equal to, you will have endemic. So that's a prediction we can do using model, okay? Does it make sense?
So when does it become epidemic?
When this ratio is greater than 1, it will become endemic. Because we know if it's less than 1, it will disappear. Then what's left is the other situation. Then it has to be endemic. Mm-hmm.
It doesn't seem intuitive that it depends on total numbers of the size of the population. But it does.
Yeah, because that's what the MS tell us. Okay. After we do the bunch of lots of iteration, okay, we eventually find this number. Okay. So if you want to interpret, okay, this number, which means if you have n here, okay, if n is large.
Yes, also, you have to have a boundary for the n within a city or something, right?
Yeah.
Yes, you can't make n.
You can actually interpret, okay, each term in this in this ratio. If I have a large number n, this ratio will increase, right? And if the population size increase, there are some people I will get more and more difficult to infect because they spread out too much.
But there will also be more susceptible.
Yes, but considering that infection occurs at a rate, okay, you just consider the distance, how the infection travel, okay? If you have a large size, even before this infection can travel to the other end, some people already recovered. That's why. Actually, you can interpret all the terms in this ratio, okay? This is a word, not a very actually exact word, okay? So it can be endemic or epidemic, okay? Okay, if you are confused, sorry, yeah. So that's what I mean, actually. It can either be endemic or epidemic, okay?
In general, there are two states, disappearing or not disappearing.
Mm-hmm.
And not disappearing.
Yeah.
That's why there's
Mm-hmm.
endemic, epidemic, and pandemic.
Yeah, you can call this not disappearing, okay?
Yes.
Okay, if that makes you more comfortable.
That would make sense.
Yeah.
Okay, so this one is disappearing, that one is not disappearing, okay? Make you happy now? Okay. No, don't be sorry. I just, I think you have a very, specific definition for endemic or epidemic, so, but to me, okay. I just roughly divide them into two categories, okay? But anyway, that's what it is. So similarly, you can think about what if the beta changes? That's the infection rate. What if the infection rate changes, and what our ratio will do? Okay, increase or decrease, and why is that? And how is actually connected to the disappearance or not disappearance? Okay. So you can actually interpret everything there. So that's good. So we actually did a prediction. Okay, that's a prediction. Model prediction, okay? We are always talking about model prediction, okay? That's a prediction. So first example. Now, let's move on, okay? we talk about the SI model. We talk about the SIS model. Okay. Now we're gonna talk about the SIR model. Okay. So now we have 3 subpopulation. Okay. We have susceptible, we have infective, and we have removed or recovered. Okay, people sometimes call it removed, sometimes call it recovered. Okay, they're the same thing. So the reason we have removed the subpopulation is because some subjects can be isolated, okay, from the rest population, or they can develop a lifetime immunity against the virus infection, measles, right? You have, after vaccination, right, you have a lifetime immunity, almost. So, yeah, it could be death too. That's our next model, okay? Right now, we don't have birth. No, we also didn't consider a death, okay, in the model, okay? Not yet. So, how we derive the model? If we have this, now we can do the same thing, right? This time let's start with diagram, okay, instead of the equation, okay. So we know the S can become I at the rate beta Si, right? And now we have another population, R. So the infective can become recovered or removed at the rate gamma I. So anything else? Make it simple. That's all we have now, okay? S become I become R, okay? And we know the rate. So what's the equation for S? Right? Decrease of S due to infection. So what's the equation for I? Increase of I due to infection and decrease of I due to recurring. And what's the equation for R? Increase of R due to recurring. That's it. So is diagram modeling much easier than the equation modeling? Yes. That's because you already know, okay, how to do the equation. Okay. Otherwise, you will not derive the equations from the diagram. Okay, that easily. Okay. So that's our equations. Again, we play with this model. Okay. What we can do is that actually we can still make the assumption because we assume there's no death, there's no birth. Okay, because we actually didn't consider any death or birth in the model yet. Okay, so we can actually now play with the model. Again, we want to answer a question: when will an epidemic occur? Or let's say not a disappearing, okay, occur. How we do that? First, we interpret this question into what? Mathematical expression. Okay. So again, we know if the slope is greater than or equal to 0, then the infection will not disappear. So that says beta Si minus gamma I should be greater than 0. So that's what it is. But now, okay, it's not as simple as what we do for the 2-equation system. Okay, now we have 3 equations. Okay, so the math will be a little bit more complex. Okay, than what we did for the 2-equation system. So I will skip the detail. Okay, but if you're interested, okay, you can actually start from here to derive, and eventually you will get some conditions like this. So here, instead of n, we have S0. S0 is the number of susceptible at the initial time point. Okay. So now, this actually looks very similar to the R0, right? We just defined the reproductive ratio, right? So the difference is just here. Instead of n, we have S0. So can we interpret this ratio? Let's say if S0 increase, which means the initial number of susceptible is large, right? Then this ratio will increase too. So if the number of susceptible is large, is that likely to develop endemic or less likely? More likely, right? Then that matches our question, right? So under this condition, it's more likely to have an endemic or epidemics, right? So you can play the same game, okay, with beta and gamma, okay. What if the infection rate increase? Of course, it will be more likely to have endemic or epidemics. And gamma is a recurrent rate, we know. And if the recurrent rate is small, then more people will suffer from the infection longer, right? Then you have a bigger chance to have endemic or epidemics. So actually, you can interpret each term, okay, in this model. That's how we actually think in model. Okay, so we play with number. We look at what if the number changes, okay, and what's the consequence. So that's this model, and now let's make it more realistic, okay, like what I did for the infection model. We haven't considered the birth and death, okay, for quite a long time. And you are not satisfied with that because we know for long-term infection like HIV, okay, we do have death and birth. Some babies are actually, they're infected, okay, since they're inside of the, you know. So,
You're not introducing any other parameters like immunological memory or something like adaptive immune system where the infection.
That depends on how complicated you want the model to be. Okay. For example, if I want to add the memory immunity into a model, yeah, I can do that. But that model will be more complicated than what I just talked about. Okay. So, like what I did here, we haven't considered the birth and death, but now let's add the birth and death. Next, what I can do actually is, what if I add virulence evolution into the model? Okay, so that's actually the next 2 models I can talk about.
Since you're talking about the long-term infection.
Yeah. Yeah. So when we talk about long-term infection, sometimes we also consider the virulence evolution, right? So that will be, you can add this kind of factor one by one, okay, by starting with the simple model. No. So now let's back to the, this question. So now we want to consider birth and death. Let's start with diagram again. Okay. We have S, we have I, we have R. So, like before, we have infection, right? And we have recurring. However, now we have also have birth. And let's make it simple. Let's assume that we just give birth to S. Okay, we don't want to yield baby. Okay, let's say that way. Okay, so the whole population will give birth to S. Now, either S, I, or R, they can die, right? Let's say the death rate is D. Does it make sense? Okay, so D here is actually the average death rate of the whole population. Okay, the death rate of the whole population. Also, we should have disease-associated death. Right? That actually makes more sense, right?
Why do you want to separate it from R?
If that confuses you, okay, I can draw this way. It's just death. And the direction of the arrow actually means it's decreasing or increasing. Okay, so it doesn't matter you draw it up or.
Yeah, but death is this death that is regardless to the infection.
Due to infection?
The infection can be included in R. So we remove either if it's resistant or death.
Let's say we have three reasons that could lead to the decrease of I. This is a disease-associated death. This is recurring. This is just the general, okay, the death of the the ordinary population.
So does that mean that the S
Which means
are the same?
which means this population will die faster than the other two populations.
So they're
Does that make sense?
So the term R is confusing, that's why he's raising the point.
Yeah.
It's a removal for
This causes recurring, okay? Or removing. Removing means they're isolated or they develop the lifetime immunity. Okay, there's different pathway. Okay, it's not a disease-associated death caused. You wanna if one subject die due to the disease, you wanna become R. R are live people. Okay, we are not counting dead people here. Okay, so all the S, I, R, they are live people. Okay, they're not dead people. So does that answer your question? Okay, so not just actually we'll model the people. Okay, when we model cells, usually we just model the live cells. Okay, we actually don't model the dead cells.
in case of other cells.
Yeah, that's true. I think what I'm thinking actually is yeah, what I'm thinking is like a CFSE. Okay, if we label the cells using the CFSE, what we measure is just live cells, and what we model is also live cells. Okay, so we don't actually model the dead cell. So now we have the diagram. So can you write down the equation? Try. Like we just did for quite a few times. Don't look at the slide. then you're right.
So when you do the BN,
Mm-hmm.
the rate of
Just use BN. Okay.
they're all coming from the susceptible population. They're
So-
not coming from the I or R.
No, when I write BN, which means both S, I, and R, they can all give birth to new babies.
So it refers
Okay.
to the whole population.
Yeah, that's the whole population. And let's make it simple. We just assume that all the newborn baby are healthy. Okay, even they are from infective, parents.
So it's
Down.
very hypothetical condition.
So if you're done, then look at the slide. Compare what you get with what's on the slide. You don't need to worry about n for now, okay? Just write down the equations for S, I, and R. No, it's not. So just consider the increase and the decrease, okay, of the number due to what factors? Okay, all set. So how many of you are satisfied with your modeling? Raise your hand. Okay, probably 1/3. Okay, that's actually a good score after just 2 hours, okay, of training. So how many of you are 50% satisfied with your modeling result? More than 50? 50 to 100%, okay. Okay, that's another sort of 1/3, okay. So what's left is either more than 100% satisfied with your result. Okay, that's my interpretation, or so. But anyway, by comparing your result with the model here, if you find any mismatching term, find a way to correct them. That's all. Get it right eventually, then I think that serve the purpose. Okay. So comparing the equation with the diagram we have here. Okay. Comparing these two, you can match each term with each term in this diagram actually. For example, Bn, we know Bn is here, and it goes to S, right? And beta Si is here. It causes the decrease of S, so we subtract it in the equation. So thinking a diagram, then you can actually match, okay, the equation and diagram. That's all you need to do, okay? So do you need a few more minutes, or let's just talk about the next model? Okay. Now we can also do something, okay, with this model. Although right now we have birth and death, so the total number of the subjects in this population will not be a constant anymore. Okay. So n here is not a constant anymore because we have birth and death. Okay. However, after we derive this model, we have to do some simple checking. Okay. For example, we have to make sure that the relationship between B and D. So if we look at the steady, so-called steady state, which means all the derivatives become 0. Okay. The definition is simple, okay? Steady state means all the derivatives become 0. So the left-hand side is derivative, the right-hand side is f. So f also becomes 0, right? And we can solve these equations and get the solution for the state variables, okay? For SIR, that's what we have in the equation, right? So from here, we have a bunch of equations, right? For our model, we have 4 equations actually. Okay, one equation for S, one for R, one for N. And we let it to be 0. That's what you get here. Okay, then you solve this equation for S, I, R, and N. That's the result. That's so-called steady state, which means the number of S will stay as this number. And this means the number of I will stay as this number. Okay. So by looking at this, let's check the positivity. Okay. If we want the number of I to be greater than or equal to 0, then B has to be greater than or equal to D. That makes sense, right? Because B is the birth rate of the whole population, and D is the death rate of the whole population. If the birth rate is greater than or equal to the death rate, then this whole population can survive. Otherwise, you will have a extermination of this whole population, right? So because this model is a little too complicated, so I will not bother to derive the productive ratio, okay, like we did before. However, there are some simple things, okay, you can check with this kind of model, okay, by considering the steady state. And we're going to talk about the steady state actually a little more later, okay. So now let's consider this model. We have considered the birth and the death. What if the virulence of the virus will evolve? Okay, how are we gonna include that model, okay, into this one? Incorporate that factor actually into this model. So the first thing we're gonna do is actually interpretation, okay, how to interpret our question, okay, into mathematical expression. So let's start with diagram, okay? But before we draw a diagram, we need to introduce what? Introduce something we can compare the virulence evolution, right? For example, we have a wild type virus. Then we have a mutant virus, okay? If we have virulence evolution, then we were expecting that the mutants will infect more people than the wild type. Does that make sense? Okay, so now let's introduce some new notation, okay? For the wild type, okay, we denote the number of the infective as I, okay? It's the same notation. And its infection rate is beta. The recurrent rate from the wild type virus is gamma. And the disease associated death rate is C for wild type virus. Okay. For the mutant, we denote the number of population as I prime. Okay. And it has an infection rate beta prime. Similarly, gamma prime and C prime. Okay. So now we have two distinct infective population, right? One is I, one is I prime. So if I draw a diagram, it becomes a little bit more complicated. So now S will either become I or become I prime, right? So we have I or I prime. So at what rate? This one I have a rate beta Si, right? And this one we have a beta prime Si prime, right? So the recurrent rate, similar thing, okay? This recurrent rate is gamma I, and this recurrent rate is gamma prime I prime.
Right. You are assuming that the recurrent rate is same for
No.
Newton minus.
No, no. This is gamma, this is gamma prime. They're different.
Oh yeah, okay.
Okay. So we also have a disease-associated death, right? For this one, the death rate should be D plus C prime, I prime. Right? And for this one, then this should be D plus C and we also have a birth. And death of S and death of R. Okay, so does this model make sense? So now we consider a lot of things, okay? Infection, recurring, death, birth, and now we have what type of the mutant virus, okay? For example, if you want to study influenza, okay, this some model you can use actually already can work. You can use it in real problem. So how about we write the equation? Try, okay? Okay, if you're done with your own model, compare the model on the board, okay, with your own answer, okay? Or you can just start copying it. I'm just kidding. But anyway, do the same thing, okay? Check what are the factors that cause the increase of SIR, and or what factors cause the decrease. That's all. Add or subtract. That's all you need to do. Just don't miss any factor. That's all, right?
So the graphical representation play a very good role.
Mm-hmm.
So this is the basic foundation in which you can easily derive the mathematical equation.
Yeah.
And this is correct.
Yeah. When I derive a model, I write the equation first, then draw a diagram then. But you can actually do a diagram first, okay, then write the equation. That doesn't matter, okay, the order. Whichever is more, easier, okay, is easier for you.
How we practice art and
For you, for if you just start to do the modeling, I will recommend it this way, okay, instead of thinking in the equation, okay, because you need to actually get very familiar with the terms. That will be easy for you. Otherwise, I will recommend to start from here. Okay. Draw the diagram. Draw the relationship between, different components, factors, and write down the rate, and then you go ahead with the equation, okay? So, can we play with this model to do some prediction? Yes, of course. Now, remember, our purpose to develop this model is to predict under what conditions the mutant virus will take over the wild-type virus, right? You can actually do the similar thing as I did before, derive some ratio, R0, right? Under what condition, if it's greater than 1, then this one will win, and this one will lose. You can do similar thing, actually. And but however, the problem is this model actually is much more complicated than whatever model we wrote down before. So I will not bother to actually derive the whole thing on the board. It's going to take half an hour. So one easy thing you can do is play with the parameter using numerical solvers. Okay, you can change each parameter, see how the system will respond. And you will actually, by visualization, find some parameters that this mutant will win, but this one will lose. For example, you can change the infection rate, right? You can fix this one. For example, if you know the infection rate of the wild-type virus, then now I can just change the infection rate of the mutants. And then I can tell if this mutant virus infection rate is greater than what kind of threshold, then this mutant virus will win. Okay, so that's kind of the that kind of game you can play. Okay, also you can change some other parameter, for example, the recurrent rate or the disease-associated death rate. Okay, so you can play them one by one. Okay, and to see under what conditions. But if you are confident enough to do the mathematical derivation, then you're okay to go ahead and derive some ratios. Okay, like what I did before. So actually there is some ratios. Okay, you can actually use. I cannot just write down the answer for now. Okay. This is actually the condition that the mutant virus will win. It makes sense, right? If the infection rate is greater than the infection rate of the wild-type virus, of course, you get some advantage, okay? Similarly, if you look at the recurrent rate, the disease-associated rate, okay? This is not inference. This is more like a prediction. Inference, usually we use the word inference, which means we usually do statistical inference. That means we feed the model to data to get the parameter estimate. Okay, that's usually people call it inference. And this way, more like call it prediction. So under this condition, we can predict that this mutant virus will take over the wild-type virus. Okay, that's a prediction. Okay. So, question?
This rate of the I prime shouldn't be D prime.
No. This D is for the whole population. So see, here is D. Here's D. Here's D. Yeah. That's sort of the baseline death rate. Okay. So that's why you have C prime and C. Okay. These are different. Okay. So now we actually spend 1 hour to finish. Actually, we finished the epidemics course. Okay, in 1 hour. Okay. You need actually a whole semester. Okay, to learn all this SI, SIS, SIR model. Okay, we finished in 1 hour. Okay, and I have to say it's a little bit rush, but given the time we have, okay, so we actually accomplished a great thing. Okay, I have to say that. So we still have half an hour, and I'm gonna talk some, easier stuff. Okay. Now you don't need to worry about write down equations. Okay. Let's just look at the slides. So we have talked about the SIR model and the infection model and the growth death model, right? Now they're all single compartment model. Okay. Now I just want to show you an example what I mean by multi-compartment model. Okay. This is a recent work we did actually. After the primary influenza infection, we want to understand what these cells, okay, immune cells do, okay, within each lymphoid organ, and also what they do, okay, how they migrate, okay, at what kind of rate, okay, between, okay, a pair of organs. So here the blood compartment is the heavy, and the organ we consider here mainly is the bone marrow, spleen, lymph node, and lung. And lung is the infection site. And here the arrow here actually means the direction of the migration. Okay, this migration is bidirectional. Okay, this one is also bidirectional, which means the cells can go from the blood back to lymph node or from lymph node to blood. Then bone marrow will take the plasma cells. Okay, we know that. Although we know the lymphocytes, okay, they are generated from bone marrow, but for the short time window, we neglect that. Okay, and infection site, they only take the immune cells. Okay, very specific immune cells. They do not actually send that back. That's chemokine. Okay, issue. You have a high concentration of chemokine. Okay, at the infection site, and you have an inflammation, and that's why we assume that the cells will go just one direction. Okay. Of course, you can change the assumption. Okay. Whatever you're not sure, you can change this to bidirectional, and let the data to tell you whether that should be one directional or bidirectional. So that's what we call the multi-compartment model. And the first, this is actually a general framework we developed. And one specific work we published actually is to look at the migration of CTL. We also look at the proliferation and disappearance of CTLs within each compartment, and then we also consider the migration, between a pair of organs. And here we neglect the blood compartment because we don't have observation, in the blood. But we know that all the cells will have to go to the blood first, then go to the different organ. That's generally true. Okay. So for this model, I don't have too much time to talk about the details. What I want to show you here is that if you have time later, you can go through the slide. And this kind of model is actually constructed in a similar way, as what we did here. Draw a diagram. See, I draw a diagram. And then for each term, I look at the factors that lead to the increase or decrease. Then I put that in a model. That's it. So that's exactly what I taught. I do the same thing. So also here, there are some tricky things that I have a delay term. Remember, we learned the delayed ODE. It's called the DDE. So here I actually use the delay. So that's a real example for the delay ordinary differential equation. I think by reading the legend, you can easily understand which term is what. So I will not spend too much time on that. So here are some remarks that I want to remind you. First, the parameters can be a function of other variables, and it can also include a delay. And we assume the one directional migration. However, this model parameter can actually account for bidirectional migration. For example, when we assume that the migration from blood to bone marrow is one directional, I can write my model in this way, okay? It's migration in minus migration out. Okay, then here is my net rate. Okay, what I use actually is a net rate in my model. And if I write my model in this way, I have a problem, identifiability issue. These two parameters stay together. You cannot distinguish them. Okay, so that's why I say this. Okay, here. So remember the gross death model we talked about before, rho minus delta. Okay, same thing here. That's what I mean. Based on different assumptions, okay, you can generate actually more model structures for the same problem. Actually, based on this diagram, okay, we did actually generate more model structure. I can show you later, or let me just show you now. Yeah, for example, here, this is our first model. Okay, that's the model I just showed you, and then we actually have 3 more models. Okay, based on different assumptions. So you want to use data to actually select these models to see which assumption is more has been supported more by data. Okay, that will be something called model selection or model comparison. Okay, go ahead.
There are obviously like a lot of parameters that you can put in the model. How do you decide what's important enough?
Oh, that's a good question. When we decided which parameters to include in the model or which not, that has to depend on our knowledge about the biological problems. If I think the proliferation is important or migration is important, I should include that in the model, of course. Otherwise, I will make the wrong model structure, right? And sometimes if we are not sure, okay, whether we should include one parameter, we have no knowledge about that. My suggestion will be include that term in your model, and then later you let the data to tell that term is significant or not. Okay, and that also can be done by using the model selection technique. Okay, I'm going to talk about the model selection in a few minutes. Okay. So now, before we talk about the more advanced technique, okay, I want to actually mention some, terminology. Okay, you may want to know. Okay, the first one is called fixed point. Actually, we already know what's a fixed point. Remember, for the steady state, okay, we let the derivative to be 0. That means f is also 0. Then we solve this equation for x, like what we did for the SIRS model, right? Then the solution to this equation is called fixed point. Okay, it's just terminology, or you call the equilibrium point. The reason it has this name just because it's for steady state. And also you may meet these two terminologies. Okay, one is called attractor, one is called repeller. So basically, the concept is that if I have a fixed point here, if I move it a little bit away from his exact position, okay, then if the solution just go away, okay, move away from the fixed point, then it's called repeller. If I move this fixed point, but the system actually can go back to this fixed point, we call it attractor. Okay, basically this can tell you what's the stability. Okay, stability of this fixed point. So if you disturb or perturb the system a little bit, okay, after you disturb the system a little bit, will you stay at the original place, or you will just move far away from your fixed point? So that's the concept of attractor and repeller. Is that clear? Okay. So sometimes you will find some, fixed point that along certain direction it will move towards this fixed point, but along other directions you will move away from this fixed point. This one is called a saddle point. Okay. So it's not really a attractor, or it's not also a pure repeller. So this kind of thing is called a saddle point. Okay, it's possible actually. So the next thing I want to mention is something called chaos. Okay, this is a very famous example, Lorentz model. Okay, and you only have 3 equations. However, these equations, they are extremely sensitive to initial conditions and parameter values. Okay, if you solve it, okay, you will get this kind of trajectory. So the solution actually just jump between, randomly jump between these curves. Okay, this is still a attractor because the solution will not move away from this, butterfly shape, disk. However, the solution within, this butterfly shape disks, they can actually randomly jump. Okay, that's called chaos because they're extremely sensitive. So a small numerical error in a computer will cause the change of its track. So that's what it means. Okay. So eventually, there's something called phase plane. Okay. That's more like a visualization technique. That's actually how we find the attractor and the repeller here. Okay. So the idea of phase plane is that in the phase plane, if I have 2 variables in the system x1 and x2, then I use them as my coordinates. Okay, then you get a 2D plane, right? The x-axis will be x1, the y-axis will be x2. Okay, you get a 2D plane. And at each point in this plane, I draw the derivative. Okay, that's a 2-dimensional vector. It has a direction. Okay, for example, -1, -1. If I draw its vector, it should be here. -1, -1. Then I draw arrow, point to that direction. So that's a vector, okay? And if you have 2, 2, then I will draw a vector in this direction, right? From the origin to this point. Okay, that's the direction of the vector. So in other way, you can create a phase plane plot, which will look like this one. Okay. At each point, you plot the derivative, and this one we can tell it's actually a repeller because they are moving away from this fixed point. And here, same thing, okay? Although they may not just go, in a straight direction, okay? Here you actually have a spiral sort of thing, okay?
So you can model things such as chemokine migration on that.
This is more like a visualization, okay?
Okay.
It's just a plot, okay? Plot the derivative at each time point, and then you get a visualization of what the behavior of the system will be like around the fixed point. Okay, so that's a phase plane. And actually, if you use some packages, okay, it can actually draw the phase plane for you. Okay, you don't have to write code to do this. So now let's talk about 2 things. Okay, the first one is so-called identifiability analysis. The second one is called sensitivity analysis. So the so-called identifiability analysis, okay, mainly arise due to the lack of observations. Okay, we talked about a simple case of identifiability before. That's P, right? In this model, I measured the we measure the t. However, these two parameters, they always stay together. So we cannot distinguish them, right? That's one reason for identifiability issue. Another reason for identifiability issue is if we look at this model, okay, we have measurement for t. No. We have an equation for t, t star, and v. We have three equations, right? Three variables. This is infection model we actually derived, right? Like 1.5 hours ago, okay? So the problem is we may only measure the viral load in clinical study, or we measure the total number of T cells instead of measure T and T star separately. Okay, that's usually actually what people do, okay, in practice. So let's consider the worst case, okay. If I have three variables, three equations, but I only measure one of the variables, how many parameters we can actually uniquely determine from data? That's a question the so-called identifiability analysis is trying to address. Because you have that many variables, but you have this many measurement, you cannot expect that with limited data and observation, you can actually figure out all the parameter values, right? So in that case, you have to verify what parameters you can identify from data, what you cannot. If you don't do that, the consequence will be if you feed the data to model, you still get a parameter estimate, but the values could be all wrong, okay? That can be totally wrong. Even if you look at the fitting result, you say, oh, it fits pretty well. Yeah, it will, because you have more parameters than data, okay? Then you're supposed to fit the data well, okay? But all the estimates will be wrong, okay? So if you interpret your biology, okay, based on that estimates, you will get very wrong, conclusion. So that's actually one of the dangerous things, okay? You should try to avoid, okay? So systematically, okay, when we do the parameter identifiability analysis, okay, the idea actually is not complicated. So, for example, in this model, we have three variables, t, t star, and v, right? And we have parameters like rho, beta, pi, delta, doesn't matter, okay? So what we want to figure out is whether these parameters can be uniquely identified based on the data given the measurement of v, right? We only have measurement of v. So the idea will be, if I don't know t and t star, then I have to figure out a way to remove them from the system. So if I think we have a system with parameters, okay, we have input to the system, we have output of the system, okay. We know the input because that's what we designed, okay, that's what we want, right? And we know the output because we measured it, okay. And what's hiding there is the parameter values and some unmeasured variables, right? So what we want to do is remove the unobserved variables from the system and only keep things we know and the parameters. We keep the known input, keep the known output, and also we keep the parameters. Then we can actually generate some equations of our parameters and our known output or measurement. So we can actually generate some equations, okay, from the original system. So you get this kind of equation. After you get this kind of equation, then you try to solve it to say whether you have a unique solution to the parameters. So that's the basic idea. So you remove t and t star from the system. That's something you don't know. You only leave the parameters and the measured variable, and you form an equation, okay. Then you solve for parameter in terms of v. That's how you verify whether these parameters can be identified or not.
If you combine T and T star,
Mm-hmm.
total T,
It still,
for total T.
it still will be better than nothing. Okay, if we know T and T star, then it's better than, you know, you don't measure both of them. Okay, and for now, since we have this measurement, what I can do is actually define another variable, T total. Now what I'm going to do is that actually remove. Still, I'm going to remove T and T star, but I will try to keep T total here. So you keep the things you know, okay, and parameters. So for our model, this is just basic concept, okay. The concept is simple, right? You just figure out a way to remove T and T star. Then what's left is just what you know and the parameters, okay. So, question?
You may be going to be talking about it. Why are you equating that to 0?
Because I said you can generate equations for parameters, okay, and what you know. For example, this equation can be theta is equal to v plus v dot. Then if I move this to the left-hand side, I get a 0, right? You can always, transform equation, into this form, right? By moving them around, okay? So how we do this? Actually, this one is not easy, okay? To actually implement this idea is not easy. If we use this example, okay, what I'm gonna do, I need like 5 minutes to write down the, the steps, okay. But the basic idea is that I can start from V. So this is what I measured, right? And this one I don't know. Then I have to remove it. So how to remove it? I can take a second order derivative of all the variables. So take one more derivative of the variables. Then, do we have an equation for T star dot? Yes, we do. That's in your system. No, I plug in. Okay. Now, after I plug in this one, you have beta TV minus delta T star, T star. Now, beta is included, delta T star is included. But the problem is now you introduce T here, and you still have T star here, right? So here's the tricky thing I'm going to do. We actually know T star from here. From here, I can write T star is equal to I cannot use this relationship here because you plug in the same thing to the original equation, you get a circle, okay? You will not solve anything, okay? You have to take a derivative and then use this one, okay? Now, I can plug this in to here, and then I can do same thing to T. I take another derivative, and then I can incorporate our first equation into here. That's how we do it, okay? So it doesn't matter, okay, you didn't get this, this technical detail, because it does require actually skills in mathematics. But eventually, what we will, for this model, okay, we will derive actually a pretty complicated expression, okay, and we will find that for this system, if we only measure V, pi will be gone. This parameter will be gone. Which means what's left is an equation of rho, beta, delta T star, CV, and V, and its derivative. and pi is gone. And what does it mean if pi is gone? It means when you estimate the parameter values, it doesn't matter what's the value of lambda you fixed. You can get the same estimate for the rest parameters. That sounds strange, right? We actually did the computing. We fixed the pi from 1, 10, 100, 1,000, and 10,000. We plug in this number, and then we estimate these 4 parameters. And our computing says this prediction is true. So pi has no effect on the estimate of the rest parameters. And that's what the identifiability issue, okay? That's what the identifiability analysis can do for you, okay? So, however, be careful, okay? Please do not interpret this as pi is not important. Pi is actually very important biologically, right? Pi is the production rate of the virus. Okay, biologically it's very important. However, just given this model structure and the data we have, we just cannot figure it out. Okay, unfortunately, we fixed the arbitrary number will not affect the estimates of rest. That's a good thing, right? So that's an example of identifiability analysis. And this is actually a very tricky problem, okay? A tricky example. So usually you will not have this kind of issue. Usually what you get is this kind of thing, okay? You can easily tell, actually. So this is actually a very tricky issue, okay? Example. So let's skip this more, identifiability analysis technique. Let's talk about the sensitivity, okay? Sensitivity analysis, actually, conceptually it's simple, okay? By definition, it's just what if I change the parameter a little bit? What will be the change in the output? Okay, that's all. So the definition of sensitivity is that, for example, even I don't need to use an ODE model. I just use any equation, okay? Closed form solution. What if I change the parameter, okay, from 0.2 to 0.25? Okay, and what will be the change in the output? Okay, so sensitivity is defined by the change in the output divided by the change in the parameter. That's a ratio. Okay, so its general definition is here. So the output, the change in the output divided by the change in the parameter. That's called a sensitivity. So if you change a parameter a little bit, and the output changes a lot, which means the system is very sensitive to this parameter. On the other hand, if you change parameter values a lot, but the output is almost the same, which means the system is not sensitive to this parameter. Does that make sense? Okay. So can you give me some example that a system will not be sensitive to a parameter? Just construct some model. Think about some model. Okay, how you parameterize a model? That actually can easily be done. For example, I put theta here and divide by a very large number, right? And then even if I change theta from 1 to 1,000, that's 3 orders of magnitude change. The ratio will be small, okay? So it's not likely for this term to have a, impact on the output. So the system will not be actually sensitive to this one if I define my theta prime as this ratio. That's actually some example you can easily think about. So For ODEs, okay, you can also derive something called the sensitivity equation, okay. So you can actually look at the sensitivity at each time point, okay. By doing the differentiation, okay, you can derive this equation, and you can just use any solvers I just mentioned yesterday, okay, to solve this equation. You can get this solution to this sensitivity equation. Then you can look at the sensitivity of all of the. And this is model actually I mentioned yesterday, right? I changed the infection rate, but the peak of the wire load is almost the same, which means the peak wire load is not sensitive to the infection rate. However, if I change the production rate, the magnitude of the wire load peak change a lot. Okay, so that will be an example of this, sensitivity of parameters. So now let's talk about the model. Use the last 4 or 5 minutes to talk about the model comparison and selection. You have noticed that for the same problem, we can actually develop many different model structures, right? Based on what kind of factors we want to put in the model, and also based on what kind of assumptions we made. However, since we have this many options, okay, we want to know which one is the best. Or that's what we call the model comparison and selection. So the model comparison and selection, usually we do it using the so-called model comparison criterion, okay? AIC, BIC, and AICC. AIC stands for Akaike Information Criterion. Akaike, of course, by name, he's Japanese, okay? Akaike Information Criterion. BIC stands for Bayesian Information Criterion. And AICC actually is a corrective version of AIC, okay? So here, N is the total sample size, which means how many data points you have when you fit a model. Okay, K is the number of parameters you are estimating. Okay, so RSS is a residual sum of squares, which means it's after you fit a model, you calculate the distance between the data points and your fitted curve, and take a square, add them together. That's what it means by RSS. Okay, so that's a fitted residue. Okay. And this one tells you how well your model fit your data, and also tells you what's the noise level. Okay, even if your model can perfectly, fit the true output, you may have noise. Okay, noise term will be also included in here, and this term tells you how complicated your model is. If you have more parameters, you have a more complicated model, right? And this one tells you how many observations, okay, how many information you have. So this criterion actually is a balance between the information available to you and the complexity of the model, and also the goodness of fit of the model. Okay, so this kind of criterion actually balanced between multiple things. Okay, that's why people can use it. Of course, it has you can actually derive this kind of criterion rigorously. Okay, based on information theory. Okay, but that's not focused here. Okay, so you can just actually use these 3 things, and usually I will recommend this one. Okay, because this one actually has a correction for small sample size. Okay, if your sample size is small, okay, I will recommend this one. If your sample size is large, it doesn't matter actually. So we actually have an example for the use of model selection criterion. Like I mentioned before, we actually developed 4 models, okay, for the CTL migration, okay. And we calculate the AIC, okay, because actually for this case we have a large sample size, so we go with the AIC. So we calculate a number for each of the model. The smaller the score, the better, okay. That's the principle. The smaller the score, the better the model. So here, this one has the smallest score, -477. So that's our best model. The second best is the -473. Okay, so this one is the smaller one. So that's the best model. That's how we actually use the model selection criterion, okay, in practice. Finally, let's take like 2 minutes, okay? We have lots of slides. But let me spend 2 minutes talk about the pitfalls in ODE modeling. So the first thing is that you may run into the problem that what is modeled is not what is measured, okay? Like we do the cell migration modeling for B cells, okay? We had thought that, of course, the migration part, we don't have problem, right? What we have problem is the class switching, okay? We know that the activated B cells, they can do class switching from IgM to IgG to IgG to IgA, or from IgM to IgA directly. However, when we collect data, the cell number we measured actually is the antibody secreting B cells. So does that ring a bell? If these cells are secreting B cells, secreting antibodies, they cannot do class switching anymore, right? Because their isotope already been determined. So our model is wrong, okay? Our first version of model is wrong. Later we'll have to change it. So we don't have class switch. We have to remove the class switch from the model because what we measured is not what we modeled. Then now we don't have the class switch, but we still have proliferation death or other terms and antibody production, right? So that's our actually second version of model. Just because what we modeled is not what we measured, okay? You have to change that to match the biology, okay? Otherwise, you will get a wrong answer, okay? So that's one pitfall, okay? You have to pay attention. The second one is that I mentioned yesterday, sometimes, okay, ODE models cannot work just because it has the implicit assumption that the time to event need to follow an exponential distribution, okay? But if the time to event does not follow an exponential distribution, you run into trouble. We actually verified this using CFSC data. So we know that CFSC data, we're actually trying to determine the time to division or average time to division, okay? And this is actually is a random variable because each cell may have a slightly or even significantly different time to division, okay? So this actually, the length of this time to event is a random variable. And if I use ODE, I am assuming that this variable follows the exponential distribution, okay? However, we did lots of simulation, okay, thousands of simulation run, and compared to other types of models, like Smith-Martin model, originally we start from the linear birth-death ODE model, and then we compared with the Smith-Martin Satin model published by a Stringer group and our own branching process model. So then we designed two scenarios to test this problem, okay? So what if the distribution is exponential? What if the distribution is gamma? Okay, a different distribution. We know the distribution of exponential distribution looks like this, right? And the distribution of the gamma distribution actually look like this. So they look very different, okay? So we designed a simulation study, okay, to test this. So if the distribution is not a problem, then ODE should perform well for both scenarios, right? But if this assumption is a problem, then ODE is expected to perform well for this case, but perform bad for this case, right? And our results suggest that that's the case, actually. If I make my time to division follow exponential distribution, ODE actually can perform well. But once I change it to gamma distribution or log normal distribution, the performance is extremely terrible, okay? If you look at the error ratio, it can be unreasonably, okay, bad. This is error rate, okay? So extremely large. Nobody can believe, okay. So that's another issue with ODE model, okay. So people actually already verified that for cell proliferation or death, the distribution should not be a exponential distribution, okay. It can be better described by gamma or log normal distribution. So that's why we actually developed the so-called Saturn model or branching process model, which actually incorporate the gamma distribution and log normal distribution. And now you can get much more reasonable results. If you use the ODE model, you will not get any results that make sense, okay? Because you will see extremely large, doubling time or extremely short half-life. So that's another pitfall you have to pay attention, okay? The distribution of the time to event, okay? You have to, if you didn't get the reasonable results from ODE model, that could be one of the reasons, okay? So I think I'm gonna stop here today and see you this afternoon in the lab, okay? Thank you.